So, in my organic chemistry experience, I was taught to memorize the stability of the carbocation. So, tertiary carbocations are more stable than secondary, which are more stable than primary. And the explanation always given to me was kind of a circular argument. Tertiary carbons are more stable because they're more substituted. Well, if you think about that, that's just kind of stating the definition, right? We know a tertiary carbon is more substituted than a secondary because tertiaries have 3 substitutions, secondaries have seconds. This really gave no insight to me in terms of understanding why a carbocation would be more stable. So what I'm about to tell you is my understanding of why these carbocations are more stable, with a big caveat that I don't know if this is actually the explanation. This may very well be wrong. But for me, it kind of makes a lot more sense than just kind of memorizing this order. It helps me understand the mechanisms a lot better. So let's look at a primary, a secondary, and a tertiary carbon. And we're going to look at the oxidation states here. We're not going to look at the formal charges, because the formal charges of all these carbons are 0. So for this carbon here, the oxidation state is -2, this one's -1, and this one is -3. Now, let's say I want to form a carbocation at this position, the primary. Well, I would remove a hydrogen. That would give me a plus, and this would bring the oxidation number down to -2. For this one, if I remove the hydrogen, form a carbocation here, I got my carbocation, and the oxidation is 0. Here, if I remove a hydrogen, I've got my +1 and my oxidation is -1. So, from my understanding, our oxidation numbers, which I'll circle here, need to be as close to the formal charge as possible, because when we form the carbocation, we're reducing the formal charge, we're increasing the formal charge by 1. So all these have a +1 formal charge on them. Now, if I have a +1 for the formal charge, but a -2 in terms of the oxidation state, this is a big gap. There's a discrepancy between what we'd expect from an ionic bond versus a covalent bond. And since this is CH, there is a degree of ionicness to this type of bond. Whereas if I look at my secondary, +1 to -1 is a smaller gap. So the formal charge is closer to what the oxidation state would be predicted. And if I go to a tertiary, it's a +1 to a 0. So we start seeing closer and closer agreements between the oxidation, which reflects ionic, and the formal charge, which represents covalent. Now, the reality is a carbon-hydrogen bond sits somewhere between covalent and ionic. So for me, the reason why you have better stability is that you are seeing better agreement between the ionic and the covalent models in terms of what the charge of carbon should be. This larger gap of 3 whole charges for a primary is a lot bigger than 1 charge gap for tertiary, which is in between the two sits your secondary, which sits at a charge gap of roughly 2 electrons. So again, maybe this helps you, maybe this doesn't, but I've never really understood why tertiary, primary, and secondary follow those stability orders, other than hearing this kind of circular, what sounds like a circular argument for me. The way I understand it is to look at the agreement between the formal charge and the oxidation state and try to get them as close together as possible.